reagents, in particular these Grignard reagents, with these species such as in the middle here, highlighting this one with this aldehyde, make this a little bit larger. So the key thing here is we have a nucleophilic carbon, and we're forming a new carbon-carbon bond, which is exciting. And then we can protonate in the end, and we're going to end up with an alcohol, for example. Or we had a variation of this, where we reacted on the top here, it says 2B, rather than with an aldehyde or ketone, with carbon dioxide. This is kind of the special case, where now rather than generating the alcohol, we actually generate here, first of all, this is a carboxylate, the conjugate base. And then when we protonate, carboxylic acid. So we're going to see this is a good way to make carboxylic acid. And we added a carbon. Notice on the left, we just had a benzene, 6 carbons. On the right, we've added a carbon. So this is going to be good, especially as we're thinking more about synthesis later on. We have ways of doing 2 things here. We introduced the carboxylic acid, and we added a carbon. We had the epoxides that we just talked about in the context of the quiz. And where we left off is with these organocuprates, or the Gilman reagents. So before we get to that, I'll squeeze it in the corner here. So today, the goal is to think about these organocuprates just a little bit. And then we want to talk about protecting groups. Normally I outline this on the whiteboard before the class, and then to help provide a framework. We're going to take a quick detour. I think it'll be useful into oxidation reactions, and I'll describe why in a minute, or several minutes, and then last into synthesis. So these are going to be the 4 main topics for our discussion today. So now for these Gilman reagents, and we just squeezed this in the last couple of minutes yesterday, we mentioned that the names are not that important, but it's now using copper as opposed to magnesium or lithium. And what was in that video was that the copper-carbon bond is much less polar. So if we have a copper, I'll point down here, copper compared to the lithium, this lower bond has a much lower difference in polarity, which is going to affect the reactivity. In other words, it's making the carbon less negative as compared to when you have the lithium, or it's making it less nucleophilic. And so these Gilman reagents actually are kind of strange at first in looking at their reactivity and their structure. For their structure, what's different is actually I have these 2 alkyl groups connected to the lithium, or shown here on the right, this condensed version. 2 butyl groups connected to copper and lithium. And whereas we'll not get into the details of the structure, but the key thing here is that this particular reagent here that I'm circling would actually donate a butyl group. So let's look at pretty much just 2 reactions with these reagents. And the first one actually kind of contradicts everything that we were saying yesterday. So if we were to take an aldehyde or a ketone, let's just take this ketone. Now we know we could have all sorts of Grignard reagents, those magnesium ones, it's going to attack at this particular carbon, form a new carbon-carbon bond, make a tetrahedral intermediate, we protonate, and we can do that now over and over again. However, if we were to take our Gilman reagent, so let's take this one, something like this, drawing the same one from the top, what you'd actually end up seeing is no reaction. And I'll abbreviate reaction by RXN. So even though these are organometallic reagents, like what we've seen with the lithium and the magnesium one, their reactivity is different. So if you're tempted, getting bored with using magnesium or lithium, and you say, I want to throw in copper to kind of shake things up a little bit, the reactivity is actually going to be different. They're useful in a couple of reactions. We're just going to mention one right now, is that they do react with organohalides. So we can take something like, we haven't used iodo much. Let's just take this 2-iodopropane and react this with this Gilman reagent. And what you'd find is that we're going to end up adding 4 carbons. So it's just 1, 2, 3, 4. So I've ended up adding those 4 carbons. Plus, we end up with our copper species with the 4 carbons plus lithium iodide. So one thing now is that this looks like it could almost be an SN2 reaction, but it's not. You could imagine that this carbon here, being somewhat the C minus, the negative species, would attack here, kick out the iodide. However, we'll show here though, but it's not SN2. And the reason for that is, you remember back with, oh, that's interesting, the magnifying glass. Sorry, I'm just pointing at random things, trying to get rid of that big magnifying glass. No, it's not working. Okay, that doesn't help. Okay, that did something that I didn't want it to do.
Can I ask a question really quick?
Sure.
Now, with the first reaction on the arrow, does the size have to do? We know that it's less. The cuprate is less reactive, but also, what about the size? Like, it can't really get in there as well. Is that anything we have to consider with the cuprates, besides just the reactivity that we spoke about before?
Yeah, that's an excellent question. And as you were speaking, somehow you made that little bubble disappear, so that's great. You're right about the sizes, exactly. Oh no, that's coming back. So we could think about, to redraw this, in terms of the size of these metal ions. You'd have lithium, you'd have magnesium, and you could imagine copper. I'm kind of exaggerating here, but certainly the size of the reagent is going to be different here. And that's going to affect its reactivity. So we've been focusing on the polarity of the carbon-metal bond, but that's, like you mentioned, that's not the only difference. And so the size certainly will have an effect, whereas the lithium is going to be a very small, it's known as a hard nucleophile, a lot of electron density, very small together there.
Great, thank you very much.
Sure, you're welcome. And another thing here is I'm going to get to it too, is that the copper species is probably complicated. It's more likely that they're reacting by a radical, and that's why it's not going to be an SN2. So yes, the size definitely plays into this. And in response to the question as to why it doesn't react, I will try to address the question here by showing you one more example here, and we'll come back to it and see if this helps. So, as mentioned, it's probably not an SN2 reaction, because you can take a aryl iodide, so benzene, and react this with this organocuprate, or this what's known as a Gilman reagent, and this actually reacts and will introduce those 4 carbons onto benzene as a product, plus the other stuff. And so these two, or this observation in particular here, reacts with aryl halides, aryl meaning benzene, right? Suggests it's not SN2, because you can use this as a bit of review. Remember back with talking about SN2 reactions, is they don't react with benzene rings or aryl halides like this, trying to turn it on its side, because you have all of these electron density around the ring, and so your nucleophile, number one, it can't attack the backside. Here, let's use a different color there for the arrow. So one, the backside is hindered. 2, there's all this negative charge around. So you have all of these pi electrons in these pi cloud here. That's going to repel the nucleophile. And then last is that the sp2 bond is stronger. So all of these things are why you didn't see SN2 reactions on something like a benzene ring, However, now all of a sudden, this Gilman reagent allows you to do a reaction where you can introduce an alkyl group on the benzene. So that means something else is happening. And so that's suggesting a different mechanism. And I'm just going to assert, because we're not going to spend the time covering it, it's likely undergoing a radical type reaction. And then to go back to the earlier question, which is a great one, is why doesn't this react at this carbonyl carbon? And we're going to see later on reactions where it does react, and it's what's known as basically reacting at a harder or a softer electrophile. Something that we're not going to really consider in our class, but it's that this reacts actually at more polarized places that have less, have a larger distribution of electron density. So it's kind of a hand-waving argument as to why it reacts, but when it acts actually as more as a nucleophile that's not a radical species, it's going to react at more diffuse, I should say, electrophiles. So for now, we're going to say it doesn't react. We haven't really gone into the details, and so if you're asking and saying, well, you didn't really explain it, it's because I haven't really explained it, and hopefully that'll be sufficient for now. I don't want us to get bogged down into the details, if that's okay. Okay? All right. So I think that's it with these